Okay, welcome. Today we're going to talk about section 7.6 on moments, centers of mass, and centroids. So we'll start with a basic physics idea of force is mass times acceleration. So for example, a pound, we saw last time, we mentioned that that was a unit of force. Is a slug, number of slugs, a mass, and an acceleration, sometimes in feet per second squared. Newton would be another measure of force. Mass there would be in kilograms. And acceleration, usually meters per second squared. If you're on the surface of the Earth, then our acceleration due to gravity is 32 feet per second per second. So for example, a 200-pound object, that is a measurement of force. Mass we don't know, but we know it'll be measured in slugs. And we'll assume that the 200-pound object is roughly at the surface of the Earth. So times 32. So the number of slugs is 230 seconds. You can do a little reducing on that one, turn it into 25 quarters, so 6 1/4 slugs. So next we take a look at the idea of the center of mass about a point. So the idea here is that we have a fulcrum point. Think of the middle of a seesaw, if they still had seesaws on your playground when you were a kid. Might be showing my age a little bit there. And let's say we have two contestants on our little seesaw, so we've got Mo and Barney. And Mo is, let's say, 5 slugs in mass. And Barney is 6 slugs in mass. And let's say Mo is 10 feet from the center and Barney is 8 feet from the center. So we want to know, okay, is this thing balanced, or is one of them going to drop, one of them going to rise? Our moment is mass times x, where x is the length of the arm. The distance between the fulcrum and the object. So for this one, our left moment for Mo, his mass was 5 slugs. His length of the arm, 10 feet. So he is at 50 slug feet. right moment. Barney's mass, 6 slugs, times the length of the arm, 48 slug feet. So this is not a balanced system here. Mo is putting down more than Barney is. Arranged the way they are right now, they wouldn't balance. Mo would drop, Barney would rise. So that might raise the question, how do you balance this? Well, reviewing what we know before, so we know that Mo is 5 slugs in mass. There's our little fulcrum point. And we know that Barney was 6 slugs and 8 feet out. So we know that Barney was 48 slug feet. If we want to adjust, let's say, Mo, we can say that he is then X feet out. And we'll make Mo's moment of 5 times X slug feet equal to Barney's moment of 48 slug feet. So X is 48 fifths. So that would be, 9 3/5 feet. So if instead of having Mo 10 feet out, if we had him 9 3/5 feet out, then the system would be imbalanced. So the next thing we look at is we kind of look at a more general case of this. Moment about the origin, M0. So the idea here is, here's our origin, the spot in the middle. We've got our little balance beam here, and we have objects of different masses at different places. So our moment about the origin for a system like this is just the sum of the individual moments. So M1 x sub 1 plus M sub 2 x sub 2 plus blah 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 plus M sub n mass sub n times x sub n. Mass 1 times x1, mass 2 times x2, mass n times xn, and then that's our moment about the origin. Add up the individual moments. If m0 equals 0, the system is in balance. Equilibrium, in other words. Our center of mass, and for the moment we'll look at just sort of an x-axis center of mass. X bar is the moment about the origin divided by m, where m is the sum of all masses in the system. All right, so we'll look at one of these on our beautifully drawn x-axis here. So at x equals 0, we have an object with a mass of 5. At x equals 4, we have an object with a mass of 20. at x equals -1, we have an object of mass 2. And at x equals -3, we have an object of mass 4. So our moment about the origin, sum of the individual moments. So mass of 4 and an arm of -3. Mass of 2. Arm is at -1. Mass of 5, but that's right on the balance point. Mass of 20. Arm length of 4. So add all those up and we get to a positive 66. So our center of mass take that moment and divide by the sum of the masses. The objects that we had were, again, 4, 2, 5, and 20. So let's see, 9 and 2, 11, 31 is our mass. So our center of mass for this particular arrangement, 66 divided by 31. So that's 2 and 4/31. So that's where we would put the center if we wanted the system to be in equilibrium. If we put the balance, if we moved it from 0 over to 2 and 4/31, then the system would be in equilibrium. The system would balance out. So next up we look at basically a two-dimensional system. So we introduce a y-axis as well. The ideas are really the same though. Just a little note though, m sub y, moment about the y-axis. So here we are somewhere in the xy plane. If y-axis is my pivot point, then really the distances that matter to me are left and right, in other words, x coordinates. So it's a little bit counterintuitive until you think of it in those terms. So we've got x coordinates for that one. All right, so let's just look at a few objects here. So a mass of 10, and we're going to park that at -3, +2. A mass of 6 sitting at 5, 1, and a mass of 4 sitting at 0, -3. So our moment with respect to y. So again, this is my balancing point. So I'm measuring how far I am from that balancing point. So our first moment, mass of 10, and from the y-axis, it is 3 units left. Next one has a mass of 4, but it is smack dab on the y-axis. It's not going to pivot left or right. And our last one, a mass of 6, and we are 5 units to the right. So m sub y, -30 + 30 + 0 is 0. So we are actually balanced here. This would balance if we put think of it as a long board all the way across here and had the weights. The plane would balance out left and right. So next we're going to sort of look at the moment about the x-axis, and just like you guessed, if this is where we're putting the fulcrum, we're measuring that up and down. In other words, we're going to use y coordinates for m sub x, moment about the x-axis. So our top left object there still has a mass of 10, and it is 2 units above where we're putting our little balance beam here. Our next object still has a mass of 4, but now it's 3 units below where we're putting our balance beam. And our last object, 6 for the mass, and we are 1 unit above where the balancing pen is. So our moment about the x-axis, so we have 20 minus 12 plus 6 for 14. So now a couple of things that we can do with this. We can find both for the x and the y where the balancing point would be. So x bar, remember center of mass, that was if we had a horizontal axis. If we had a horizontal axis, we were measuring then up and down on that. Or my apologies, I said that backwards. Moment about the, so we have a horizontal place that we're putting them on, and the balance beam then is vertical. We're using m sub y over m. So 0 over 20 equals 0. So there's one of our 2 coordinates for the center of mass for the system. Y bar m sub x over m. So that is 14 over 20. So 7/10. So our center of mass, let's add 0, 7/10. So if I put just one little pin-sized balancing point at 0, 7/10, we wouldn't wobble left and right, we wouldn't wobble up and down, we would achieve equilibrium.